All right, so today I want to go through AC circuits. So what happens when we put the circuit components into a circuit where we don't have a battery, instead we have a current that's changing with time. So if we start with a resistor, which is the easiest thing, a resistor still obeys Ohm's law when it's in an alternating current, same as it did for a battery. And so voltage is equal to the current times time. Voltage is equal to the current times the resistance. And so if we plot that versus time, the current and the resistance curves, as you see in figure B, are both in phase. They have their peaks at the same time and their valleys at the same time, just that one is different in size from the other because of the scaling factor of the current. So they're always in phase. And you'll notice in the circuit diagram, that symbol there with the sine wave, that shows that we have an AC voltage compared to what we used to have back in Module 4, where we had the long line and the short line, which indicated a DC battery source. Okay, so that was simple. What about a capacitor? Well, in a capacitor, remember what happens is we turn the battery on and the capacitor charges up. We turn it off and it discharges. So what's going to happen when we have a voltage going in and out that's going up and down, the capacitor is going to be fluctuating back, charging and discharging, charging and discharging, with the positive and negative charges flowing back and forth around the circuit. And what's going to happen is, in general, remember, the charge is equal to C times V. So if I take the rate of change of charge, which is the current, it's going to be C times the rate of change in voltage. So the charge is going to be proportional to the slope of the voltage. So the current is going to lead the voltage by 90 degrees. So that means that the effective resistance or reactance, if we write it down, so if I want to write that the voltage in the capacitor is equal to the current in the capacitor times something, that something we call the reactance, X, and I'm going to put a subscript with C on it so you know it's for the capacitor. That capacitive reactance depends on the frequency. So if we have a DC circuit, remember we turn the voltage on, the capacitor charges up, and then the current stops flowing. So that's a zero frequency, and we have infinite resistance to the circuit. So the capacitance reactance is inversely proportional to the frequency. If we have zero frequency, we have infinite reactance. If we have infinite frequency, we have zero reactance. And so the equation that we have for the capacitive reactance is that it's 1 over omega C, where C is the capacitance, and we have to put that into farads. And remember, omega is 2 pi F, where F is a linear frequency in hertz. So if I plot the voltage and current for the capacitor in an AC circuit, you can see that the voltage, which is the green line, and the current, which is the red line, are 90 degrees out of phase, so that they have their peaks and valleys 90 degrees or a quarter of a cycle apart from each other. And you see that the current leads the voltage. So the current is at its peak, so its lowest peak down here, before the voltage gets there. Same thing, the current gets to zero at B before the voltage gets there at C. Okay, so the current is leading the voltage. What about inductors? Okay, so if we put two coils together in a circuit, and I have a current flowing in coil 1, as you can see in the figure there, it's going to create a magnetic field that flows through coil 2. So if I change the current in coil 1, that's going to change the field in coil 2, and it's going to induce an EMF in it. So we have mutual inductance there. If I change the current in I1, it's going to change I2. If I change the current in coil 2, it's going to change the EMF in coil 1. That's called mutual inductance. An example of that is a transformer. Self-inductance is if we have a coil, just one coil by itself, and I put a changing current in it, it's going to make a changing field in the loop. And that changing field in the loop is actually going to induce an EMF inside the loop itself that fights against the change in current. So if you try to change the current through a loop, it's going to push back. So you get an EMF that's called sometimes a back EMF because it pushes back. That's equal to minus the inductance, L, times delta I over delta T. So the voltage is equal to the slope of the current. Whereas before, for the capacitor was the slope of the voltage. So an inductor is a circuit component that's just a small coil. It stores energy in the form of a magnetic field. The circuit symbol that we use for it is shown there. It looks sort of just like a coil. And the inductance is L for our symbol. The SI units for inductance is a Henry, capital H, where 1 Henry is a volt second per amp or an ohm second. And 1 Henry is a large inductance. Typically you'll see millihenries or maybe microhenries in a circuit. So what we said on the previous slide was that the voltage on an inductor is proportional to the slope of the current, and it's minus the slope of the current. So if I increase the slope, I get a backwards voltage. So the inductor tries to keep the current through it constant. It fights any change in current. So the inductor stores energy in the form of a magnetic field, and the energy density is equal to 1/2 the magnetic field squared divided by mu0. So if you remember back in module 2 when we talked about capacitors, we said that they stored energy in the form of an electric field where the energy density was 1/2 epsilon naught times E squared. The energy density in an inductor similarly is B squared with the relevant constant, which is mu0, and a factor of 1/2 again. All right, so what happens if I put an inductor in an AC circuit? Well, now, because the voltage is proportional to the slope of the current, the graphs will be shifted by 90 degrees, and they'll be shifted 90 degrees the opposite way. So now the voltage is ahead of the current. So if you look, the voltage peak, which is green, the voltage goes through 0 before the current does. So the current is leading the voltage. Sorry, the voltage is leading the current, or the current is lagging the voltage. The reactance, so again, if I want to write VL is equal to IL times a resistance, the inductive reactance, X sub L, is directly proportional to the frequency because it fights the change. The faster I try to change the current, the more it's going to push back, so the more its effective resistance is. So the inductive reactance is directly proportional to the frequency, so it's omega L, where L is in henries, and since omega is 2 pi f, we can also write that as 2 pi f times L. So if I put all 3 of those components together in series in a circuit, then each of those components is going to behave differently with respect to the driving voltage. Okay, so the driving voltage is going to create a current that goes back and forth, up and down, like a sine wave through the circuit, and the voltage across each of those components is going to behave as we discuss, either in phase, ahead, or behind the current. So if I put them all together, we have a constant resistance from the resistor. The inductor, when I change the inductance, the XL increases with frequency, and XC, the capacitive reactance, decreases with frequency. So if I hook this circuit up where I've got an L and a C, and I change the frequency at which the voltage is coming through, that's going to change XL and XC, but R is going to be constant. So the resistor doesn't change, XL and XC do change. Okay, so what happens with XL? Well, as I increase the frequency, XL goes up and XC goes down. So as I change that frequency, at some point in time, XL is going to be equal to XC. And so then that second term in the total resistance or impedance of the circuit, Z, is just going to be equal to the square root of R squared, because that second term is going to go to 0. Okay, so we call that point resonance. Okay, so the resonance occurs where XL is equal to XC, and the impedance just goes to R. Okay, so when XL is equal to XC, Z is equal to R, and the frequency at which that occurs we can find by setting XL equal to XC, and XL is omega L, XC is 1 over omega C, so I get that omega squared is equal to 1 over LC, or omega is 1 over the root of LC. Okay, so if I want to solve that for frequency F, I divide omega by 2 pi, and I get the equation you see there on the bottom left, that the resonant frequency is 1 over 2 pi times the root of 1 over LC. Okay, so the current in the circuit is equal to whatever the voltage is that's driving it. And remember, for AC voltage, we talk about the root mean square value because it's always changing with time. So we talk about the average value of the voltage. So the average current is equal to the average voltage divided by Z. And as we change the frequency, Z changes, and Z is a minimum at this magic frequency, the resonant frequency F0. And at that point, the resistance, the impedance of the circuit is just equal to R. So the maximum current is in the circuit is going to be VRMS divided by R, and that will only occur at the frequency F0. The height of the curve for your resonance circuit is going to depend on how big the resistor is. The smaller the resistance, the sharper this current versus frequency curve will be. And in the lab this year, you're going to do a graph where you're going to measure for different driving frequencies what the current is through an LRC circuit. Okay, so let's do some sample calculations. So here I've got R, L, and C given. Okay, so R is 20 ohms, C is 22 microfarads, and L is 50 millihenries. And the voltage, the RMS voltage from that function generator is 24 volts. So first it asks me to find the resonant frequency. So my equation is resonant frequency F0 is 1 over 2 pi times 1 over root LC. So this is pretty straightforward. What's the biggest mistake people make? You got to put that L and you got to put that C into henries and farads. So if I look at my numbers that are given, 50 millihenries is 0.05 henries, and the capacitance 2.2 microfarads, sorry, 22 microfarads is 22 times 10 to the minus 6 farads. So that's what I have to put into my equation. So it's 1 over 2 pi, 1 over the square root of 22 times 10 to the minus 6 times 0.05. And when I do that, I get that my frequency is 151.7 hertz. Okay, so that is the frequency at which I'm going to have the maximum current through the circuit. Part B asks me what is the maximum current. Well, at resonance, IRMS is just VRMS over R. So that's going to be 24 over my R, which is 20. 24 over 20 is going to be 1.2 amps. Okay, so part C. Okay, looks like there's a lot of parts in part C, so it wants me to calculate XL, XC, Z, I, VR, VL, and VC at 100 hertz. So I'm at a position in frequency where I'm below the resonant frequency, and I want to calculate all these values. So let's just go plug our numbers into the equation. So xc is 1 over 2 pi fc. So my f is 100, and we know my c, so it's just going to be plugging it in. So 2 pi times 100 times 22 times 10 to the minus 6 farads. And again, remember, we've got a heck of a lot of stuff here in the denominator. Make sure you put your proper brackets around it as you do it, or you can get the wrong answer. So xc is 72.34, or about 72 ohms. XL, well, XL is going to be 2 pi f times L. So again, 2 pi, my f is 100, my L is 0.05. Again, make sure you put it into the base units. So I get 31.4, or about 31 units or ohms. So I've done XL, I've done XC, Z. What Z is the total impedance, the square root of R squared plus XL minus XC squared. So that's equal to R is 20, so 20 squared plus 72.34 minus 31.4 squared. And let's see, I actually did XC minus XL instead of XL minus XC, but it doesn't matter because we're squaring it. And I get 45.6, or about 46 ohms. Okay, so one more thing done. What's I? I is V over Z. So my V is 24, and my Z is 45.6. So I get a current of 0.527 amps, so about 0.53 amps. So you can see here, resonance at resonance frequency, which was 151 hertz, my current was 1.2, and now I've moved down to 100 hertz, and my current's dropped all the way down to 0.53. All right. So next thing is, what's VR, VL, and VC? So let me just carve myself out an area here. The voltage on the resistor is just the current times the resistance. So I know my current is 0.53 times my resistance, 20 ohms. So VR is 10.5 volts. Okay, voltage on the inductor is I times XL. Okay, so 0.53, and my XL was 31.4. And again, remember, in the middle of a calculation, use the unrounded numbers. So I get 16.6 volts. And finally, VC is going to be I times XC. So 0.53 times 72.3. And I get that the voltage is 38.1 volts. Okay, so that's pretty much everything that you could be asked to calculate for an RLC circuit problem. All right, so what I want you to do is, here's a similar circuit just with different values for R, L, and C. So I want you to calculate what's the impedance of the circuit. So I want you to calculate the Z value at 500 hertz. What's the current at 500 hertz? Find the resonant frequency of the circuit. and find the maximum current that this circuit has. And the maximum current, of course, remember, happens when it's at resonance.